This is the conical pendulum. So it consists of a length of string, length L, anchored to a point O with a mass M hanging about at the end of it. And it's given a push and allowed to go in a circle. And so the reason it's called a conical pendulum is that um, the surface swept out by the string is a cone. Um, Seen from above, a side view, the mass is going around. I guess it should be going this way. I have it shown going in a clockwise direction. Seen from the side, you would see this view. So I'm looking at it in the side view up here, um, in the view appropriate for drawing a force diagram. And so what we have is, say we had a string of length 1 meter, and the period of this conical pendulum, let's say, was 1.75 seconds. That would be the time it would take for the rock to go around fully in a circle and come back to where it started. Let's say that the rock was 100 grams in mass, and that would mean that its weight was 1 newton. And the problem is to find the tension in the string and the angle with respect to the vertical of the string. So first off, because we're going to need it later, let's figure out what omega is. Omega is 2 pi over t. And so if t is 1.75 seconds, omega is 2 pi rads over 1.75 seconds, which is 3.59 rads per second. And we're going to use in this problem closer to correct value of g, which is 9.8 meters per second per second. So as usual, we do a force diagram. And so what I have here is at the end of the string I have the mass and the forces acting on that mass. This is a force diagram for M, is its own downward weight. And then there's a string tension along the string, so there's only two forces acting on this mass, the string tension and the mass. But I'm going to take the string tension and I'm going to break it up into a vertical component, which is Ft cosine theta, theta being the angle of the string from the vertical. And so the angle of the string from the vertical here is the same as the angle of the string from the vertical here. And therefore the vertical component of the string is Ft cosine theta. The horizontal component is Ft sine theta. It is executing, the mass is executing UCM, and so at this instant of time, it has an acceleration pointing towards the center of the circle along which it's going. And the radius of the circle on which this mass is moving is related to L, the length of the string, by R equals L sine theta. And that just comes out of this right triangle right here. So we can do a Newton number 2 in the y direction, which says that Ft cosine theta minus mg is equal to 0. My coordinate system is the y-axis pointing up and the x-axis pointing from the mass in towards the center of the circle. And so we can take this Newton number 2 equation and we can conclude that Ft cosine theta is equal to mg, or Ft is equal to mg over cosine theta. And so looking at this equation, you can see that the tension in the string is going to be bigger than the weight. The weight is what we have in the numerator here. Newton number 2 in the x direction, there's only one x direction force acting on M, and that's Ft sine theta is equal to m times a sub x. And so by Newton number 2 I know this. On the other hand, because it's UCM, I know that a sub x is equal to r omega squared. Remember, there's two forms of acceleration for UCM, v squared over r or r omega squared. And in this problem, this is the one I want. L is equal to r is equal to L sine theta, and so therefore a sub x is equal to L sine theta times omega squared. So I can take the expression for f sub t that I got from the Newton number 2 in the y direction and plug it into this equation right here. So I get mg over cosine theta times sine theta is equal to m times, and then now I'm going to, for a sub x, I'm going to substitute in L sine theta times omega squared. And so if theta is not equal to 0, we can cancel these two sine thetas. And we can then conclude that cosine theta is equal to g over L omega squared, or in other words, theta is equal to cos minus 1 of g over L omega squared. And so if we put our numbers in, 9.8 meters per second, I'm writing it as ms minus 2, divided by the length of the string, L, 1 meter, times omega squared. Well, that's 3.59 seconds to the minus 1. I'm dropping the radians because they are going to disappear. Squared gives me an angle of 40.5 degrees with respect to the vertical of the string. And the string tension is 1 Newton divided by that angle, which is 1.32 newtons, 30%, 32% bigger actually than the original tension. And so a question for you is, what is omega and f sub t if theta is equal to L to 80 degrees, and if we make the same assumption for L is equal to 1 meter? You can do that one on your own.